Welcome back to this course on continuum mechanics. Today we talk about the Navier-Stokes equations or the viscous flow equations. So let's get started. So the topics for today's lecture are as follows. First, we'll demonstrate the closed system of equations for a fluid continuum. Then using that, we will derive the Navier-Stokes equations. That is, we'll substitute the constitutive laws for a linear isotropic, that is Newtonian fluid, into the balance laws and derive the Navier-Stokes equations. And finally, we'll demonstrate to you some special cases of this Navier-Stokes equation, which are typically applicable in different situations. So what we are discussing today is typically the first lecture in an advanced fluid mechanics course. So as I said, that we are giving you a trailer into what happens when you apply the ideas you've learned in this course to a typical fluid mechanics course. So that is what we'll see today. So we're talking about the mechanical behavior of a fluid. And to characterize the mechanical behavior of a fluid, what you need to find out is that you need to find out the velocity field everywhere in the fluid as a function of the different forces acting on the fluid continuum. So that's the whole exercise. So we'll want to find out how a fluid responds to an external force field. So what we'll be deriving are called the Navier-Stokes equations. Or also known as the viscous flow equations. So let's write down the equations from balance laws that we have already learned. So the first one is the conservation of mass equation, or also known as the continuity equation. So this is rho dot plus rho v k comma k equal to 0. So this was the Eulerian form of the conservation of mass equation that we had derived earlier in this course. Next is the momentum or the linear momentum equation. So this was where we had written rho times vi dot, which is the mass times acceleration term. That's a sum of the surface force contribution. So that was sigma ij comma j, and the body force contribution, that was rho times bi. Now, of course, this is the local form of the equations. That is, these equations that we have written 1 and 2 are valid at each and every point inside the body. So this sigma that I've written here is the stress tensor or the stress field at different points inside the body. Of course, this includes the surface as well, but that typically will be specified as a boundary condition in the problem. Now there's no energy equation I'm writing here because we assume that the system is isothermal. That is, we assume that the temperature does not change, so there's no need for an energy equation separately. So let us see what are the unknowns in these equations. So in the first equation, the continuity equation, we have the density field as an unknown. So that's one scalar field to be found out. Then we have the velocity field as an unknown. So that's three scalar field components for the velocity. Then let's come to the momentum equation. So in the momentum equation, we have already accounted for rho and v, so we'll not include that again. Then we have the stress tensor field. Now this has 6 independent components, so we get 6 unknowns here. And then, of course, body force is something we need to specify or prescribe, so that is a known value. So we'll also write down the number of equations. So for the conservation of mass equation, that's a scalar equation, so that's one equation. And then we have three equations coming from linear momentum. So in a 3D coordinate system, we have three equations here because the free index I in the equation goes from 1 to 3. So that gives us three equations. Now, of course, we can see that we have four equations, but we have a total of 6 plus 3 plus 1, that is a total of 10 unknowns. So there's something more we need. And of course, we haven't taken into account the material properties. So we need the constitutive model here. So let's call that 3. So our sigma ij, as we had written in the last lecture, is minus P, that's the thermodynamic pressure, times delta ij, plus tau ij. And then tau was written in terms of the rate of deformation tensor. So let's do that here only. So tau was given as twice mu times dij minus 2/3 of mu times dkk times delta ij. Now this has 6 equations here in it because sigma has 6 independent components. And then if I look at the number of unknowns, we have a pressure field that we have generated as a new unknown. So that's a one unknown. And then we also have dij that again gives us 6 new unknowns because it has 6 independent components. It's also symmetric. So we have added 6 equations, but we have generated 7 unknowns as a result. So we need something more. Well, one is that we have the definition of D written as the symmetric part of the velocity gradient tensor. So this gives us 6 more equations, but generates no unknown here because velocity is already included as an unknown in the first equation. So let's do a calculation. So we have a total of 16 equations, and in terms of the number of unknowns, we have 17 unknowns. So we need one more equation to close the system, and we already have that because we haven't included the equation of state here. So we typically have an equation of state that gives us an equation that relates the thermodynamic pressure, density, and temperature. But since we are assuming an isothermal situation, so we can actually remove this temperature. So we get this kind of a relationship for an isothermal system. So this is coming from the equation of state. Now for an ideal gas, this could be P equals rho r theta, but that is dependent on the kind of fluid you have. So now we can see that we have one more equation here generating no new unknown. So this closes the system. So we have 17 equations and we have 17 unknowns, so they're balanced. So now our job is to derive the Navier-Stokes equations. So first we'll simplify the expression for sigma. Sigma ij was written as minus P delta ij plus, and then we had the tau ij expression in terms of dij. So what we'll do is we'll substitute for this in terms of the velocity gradient tensor because D is simply the symmetric part of L. So we'll expand this now. So this becomes mu times Vi comma j plus mu times Vj comma I minus 2 by 3 mu Vk comma k times delta ij. So that is our sigma ij. So earlier we had called the sigma ij equation as 3, that is here. So I'll now call this as 3 prime. So now what we'll do is that we ultimately need to derive the Navier-Stokes equation, which is basically the momentum equation written for Newtonian fluids. So we can see that this Navier-Stokes equation has a term sigma ij comma j. So rather than calculating that here, why don't we calculate sigma ij comma j separately, and then we'll substitute that into this equation. So now we'll calculate sigma ij comma j. So this becomes minus p comma j times delta ij, because delta is a constant, and then we have mu times vi comma j whole comma j plus mu vj comma I comma j. So now you can see that with initial notation this calculus becomes very straightforward, and then we have minus 2 by 3 mu v k comma j times delta ij. So comma j basically means that it is del by del xj. So let us expand this. So the first term, which has p comma j, stays as it is, and then we have this term here. So using product rule, we can write that as mu comma j times vi comma j plus mu times vi comma jj. You can see that using initial notation, tensor calculus is becoming very easy. And then we have this term, which again we apply the product rule. So we get the first one is mu comma j times vj comma I plus mu times vj comma ij. And then we have the third term, which is this one, minus 2 by 3 mu comma j v k comma k delta ij minus 2 by 3 mu v k comma kj delta ij. So this we'll call as equation 3 double prime, like this. So we have quite a few terms in this equation, but if I look at these terms, these two terms particularly, in fact, let's have this one as well, we can see that we have a spatial gradient of the dynamic viscosity mu in these terms. Now typically, for most of the fluids that we deal with, mu is homogeneous, because think about it, the system, the fluid is well mixed. So what happens is that there's no reason that the viscosity of the fluid should be more in some region as compared to the others. So let's say for homogeneous viscosity field, mu comma j terms vanish, because mu is not a function of space anymore. So if you differentiate mu with respect to small x j, that comes out to be 0. Of course, this is an assumption we are taking just to simplify the work and proceed. But if you are dealing with a situation where mu actually is non-homogeneous, then you'll have to retain these terms. But since for most of the fluid situations we deal with, viscosity is indeed homogeneous, so this is an assumption that is quite relevant. So with that, we'll see that we'll be left with the terms that have a viscosity mu and not its gradient. And in fact, in this term, we can apply the substitution property of delta. and that will get rid of the j here. So I can remove this and I can call this I here. And then if you look at these two terms, in the second one we have a vk comma ki. So I can write that as vj comma ji, which is also the same as vj comma ij. So we can see that it's the same as this term. So we can combine these two, and I'll do it here only. So this second vk comma ki, I'll write that as vj comma ij. And now we can see that this is mu minus 2 by 3 mu of the same quantity. So this can be simplified to mu by 3, and I can remove the last term out of this. So let's call this 3 triple prime. So this has given us the expression for sigma ij comma j, which can now be substituted into our momentum equation. So we substitute sigma ij comma j into the momentum equation. The momentum equation was rho vi dot is sigma ij comma j plus rho bi. So let's substitute sigma ij comma j here. Again, actually this term here that has pressure, we can apply the substitution property of delta. So this becomes minus p comma I plus mu vi comma jj plus mu by 3 times vj comma ij, and then we have the body force rho times bi. So I will box this because this is the Navier-Stokes equations that we were looking for. And of course, these equations have to be solved in conjunction with our conservation of mass equation and the equation of state, which is given like this. So with these three equations, we can solve for the unknowns, which are the density, the velocity field, and the pressure. So we have three equations here, one equation each here, and we have 5 unknowns as well. So this system looks closed and we can solve it to get the values uniquely. Now you may have noticed that this equation, the Navier-Stokes equation here, is a differential equation because we have derivatives. So when we solve differential equations, we have to integrate quantities, and that generates constants of integration. So to get those constants, we need some boundary conditions. So let's call these equations A, B, and C. So A to C can be solved with the rightly chosen, the right kind of boundary and initial conditions to get the constants of integration. So mathematically, these are boundary conditions, but since we also have a time variable and there's a first order derivative with respect to time in this equation, so we need the value of the functions at t equal to 0. That is typically known as the initial condition in literature. Now in the Navier-Stokes equation, we see that we have this vi dot term, that is a material derivative of velocity field, which is expanded using the Eulerian form of the material derivative as del vi by del t plus vk times vi comma k, and then we solve the equations, and you see here that we have a velocity times a gradient of velocity. So this is non-linear, and it is this term in the equation that makes the overall system non-linear. So it's a coupled non-linear system of equations, which actually is very difficult to solve in general. And it is this non-linearity particularly that gives rise to very interesting and very non-intuitive results or phenomena which we notice in fluids. Now, typically as a mechanical engineer, when I solve these system of equations for a given situation, let us say I'm solving an aerodynamic problem around a Formula 1 car, I will get the solution that is a velocity field, that's a velocity of air around my car body. I'll also get the pressure at the different points on the surface of the car, and using these, let's say using this pressure, I can calculate the form drag or the pressure drag, and using this velocity field around the car, I can calculate the viscous drag or the shear drag, and that will give me together a global quantity called the overall drag force on the car. And then I can improve the design of the car and then measure the drag again, and I keep on evolving the design so that I minimize my drag function. So this is typically how we use these quantities for something useful in design. I'm sure you can see the connect of the foundations of continuum mechanics that we have learned in this course with the theoretical ideas that we typically learn in advanced fluid mechanics. So this was the whole idea of this week, to give you some sort of a flavor in fluid mechanics, because I myself am a fluid mechanist. So I can only give you a flavor in this field, but the whole idea is that you appreciate that continuum mechanics is useful and can be applied to solve real world problems. So these equations that we have from A to C, particularly the equation number A, that's the momentum equation or the Navier-Stokes equation for viscous fluids, it is not possible to solve this equation analytically for a general case. And in fact, this problem is $1 million problem. But the whole idea is that it is not possible to analytically solve as of today this equation, and therefore we use numerical methods to solve it. But that's a separate subject in itself, to solve these equations using numerical techniques, and we're not getting into that. But typically as engineers, what we do is we apply some simplifying assumptions, and when we apply those simplifying assumptions, it may happen that the equation takes a form which can be solved analytically. So now we'll discuss some of those special cases which will reduce these equations to simplified form, which are typically discussed in a course in fluid mechanics as well. So the first case is the case where you have an isothermal situation, and we already assumed that case to start with. So that is when the temperature is a constant and there's no need for an energy equation. Another special case we consider, that's very common, is the incompressible assumption or incompressible fluid assumption. And what this means is that your density is a constant, and fluids like water, which are used a lot, or oil, which are used for hydraulics, are mostly incompressible. Of course, if you apply very high pressure to water or oil, you will notice some change in volume, that is a change in density of the material elements in the fluid. But for usual range of pressures, we do not see much of a change in the density, so we consider these as incompressible fluids. So under this assumption, what happens is that rho dot is a zero, because we're talking about an isochoric situation. So rho dot is 0. So this implies the continuity equation boils down to Vk comma k equal to 0. That's a simplified form of the continuity equation. And if you look at the momentum equation, the momentum equation was written as rho vi dot equals rho bi minus p comma I plus mu vi comma jj plus mu by 3 vj comma ij. Now if we look at this term, this can be written as vj comma ji, which is actually equal to vj comma j and differentiated with respect to I. But since vj comma j is a 0, we just showed that from here. So this term vanishes in the momentum equation as well when we're talking about incompressible fluids. So the incompressible fluid has a momentum equation of the Navier-Stokes equation which only has these terms and not the last one, for the reason that we have a divergence-free velocity field. Now the third assumption is for an inviscid fluid. Now inviscid means zero viscosity. That is, no resistance. And such inviscid fluids or frictionless fluids are actually called ideal fluids, because the aim of a fluid is to flow. So a fluid that does not provide any resistance is actually termed as an ideal fluid. So the viscosity mu is 0 for inviscid fluids. That means that you do not need any shear stress to sustain a rate of deformation because the viscosity is 0 here. And the momentum equation, the Navier-Stokes equation, simplifies to this simple form where we do not have any viscosity term, and this special case where we only have the first order gradients of terms is called the Euler equation. Now since it's a first order differential equation, not a second one, so it needs a different treatment mathematically, but we'll not get into that right now because our aim is to simply present these special cases to you. Now another special case we come across very commonly is called the steady flow case. So the word steady means that things do not change with time if you're looking at a quantity at a given position in space. So if you fix the spatial coordinate and you're looking at the change in the quantity with respect to time, let's say velocity, then what that would mean is that del vi by del t is a 0. So in the momentum equation on the left hand side, when we expand this in terms of the material derivative, we can put the partial derivative of velocity field with respect to time as 0 for a steady flow situation. Now let's talk about another situation which is called irrotational flow. Now if you recall that the velocity gradient tensor Lij was written as Dij, that was a symmetric part of it, and then there was a skew symmetric part which was Wij, which was actually called the vorticity or the spin tensor. Now for this irrotational flow, there is no rotation. That means the vorticity or spin is 0. So the W tensor is identically 0 for irrotational flow. And since W has 3 independent components, and we mentioned that we can define a vorticity vector omega associated with that. So this omega also is 0 in this case. So I can say that the vorticity vector omega is also 0. And we'd also shown that our omega vector is half of the curl of velocity field that we had shown in kinematics. So if we are saying that the flow is irrotational, which we do find in certain situations. So in these irrotational flows, basically what everything boils down to is the curl of velocity is identically zero everywhere. That's the same as specifying that the W tensor is zero. So now we have expressed this condition of irrotationality to some condition on the velocity. So let's box this. But in the beginning of the course, we also mentioned that there's an identity that the curl of the gradient of any scalar field is identically zero. So this was an identity we had shown in the tensor calculus discussion in the beginning of the course. So now using this identity, we can say that if the curl of a quantity, a vector quantity is zero everywhere, that vector quantity can be expressed as the gradient of some scalar field. So this V has three independent components, but this phi has just one independent component, it's a scalar. So this means that the three components of V are all coming from a single scalar field, so they cannot be completely independent to each other. And this also simplifies the work mathematically because we only need one velocity potential that can be used to generate the complete velocity field in the problem. So instead of solving for the velocity field, which is three scalar components, we solve for single scalar field phi, and the velocity can be obtained from that. And this is called a potential flow problem, because you can define a velocity potential. And why was it possible to define a velocity potential? Because the flow is irrotational. So for irrotational flows, we can define a velocity potential and basically use the potential flow theory for this potential flow problem. Now, if in addition to irrotational flow, you also have incompressible fluid or a flow, then incompressible was a condition on the velocity that divergence of velocity is zero, and irrotational is that velocity can be written as a gradient of a scalar field phi. So combining these, we get the divergence of the gradient of phi is a zero, which basically means the Laplacian of phi is zero, and this is an equation we solve in potential flow theory. If I write in initial notation, this can be written as V k comma k equal to 0, and V equals gradient of phi can be written as Vk is phi comma k. So divergence of the gradient of phi equal to 0 can be expressed as phi comma k whole comma k equal to 0. So this basically means phi comma kk equal to 0. So with this, we come to the end of this lecture, where we derived the viscous flow equations or the Navier-Stokes equations, which are typically used for solving fluid mechanics problems. And these equations, along with the conservation of mass and the equation of state, can be used to solve for the velocity and the pressure fields for a Newtonian fluid. And then post that, we showed some special cases, because typically we deal with flows which are incompressible, or we deal with steady flow situations or irrotational flows. So it's worth knowing how the equations simplify under those conditions. With this, we have developed our system of equations that are needed in a fluid mechanics problem. In the next lecture, we will solve for the velocity field for an actual flow situation happening on a mountain surface using these system of equations, and show you the solutions for the velocity and the pressure fields as a result. So thank you very much, and I will see you next time.